I'm a PhD student at University Paris-Saclay. I'm in the parietal team and my supervisor is Bertrand Thirion. Today I'll present my work about modeling shared responses via MultiView ICA. This is a joint work with Luigi, Gresele, Aapo, Hyvärinen, Bertrand Thirion, Alexandre, Gramfort and Pierre, Ablin. First, let us focus on this problem where two sources are emitting a signal that is recorded by two sensors. This can be seen as a model of magnetoencephalography, where magnetometers record the signal emitted by activated neurons. Because propagation time can be neglected, the signal recorded by the sensors can be seen as a linear mixture of the signal emitted by the sources. S is the vector of sources that are assumed to be independent. X are the recordings, and A describe how the recordings is modeled as a linear mixture of the sources. At first sight, this model may seem ill-defined, because if we take one source and multiply it by some constant, and take the corresponding column of A and divide it by the same constant, we'll get another set of sources and another matrix A that describes X just as well. Similarly, if we permute source 1 and source 2, and column 1 and column 2 of A, we'll also get another set of sources and another mixing matrix that describes X just as well. However, if we assume that at most one source follows a Gaussian distribution, then the previously described scale and permutation indeterminacies are the only one. This is important because it tells you that ICA is actually a well-defined model up to some trivial indeterminacies. Now, let us consider the more general model where we record information about two subjects. They share the same sources, S, but they have different mixing matrices, A1 and A2, and different noise level, N1 and N2. The noise level are necessary in order to avoid degenerate likelihood, and we'll assume, like before, that at most one source is Gaussian. A natural solution to this problem is just to use ICA for each subject independently. But the recovered sources will differ in permutation and scaling. But there is a simple solution to this. We'll just have to scale the sources so that they have variance 1, and use the Hungarian algorithm to recover the correct permutation. Then the estimate of the common source can be seen as just the mean of the subject-specific sources. Another approach is to stack the recordings of subject 1 and subject 2 component-wise into a vector X. We then extract the first k principal components of X, yielding a vector X-red that has the same dimension than the subject-specific recording. We perform an ICA on X-red and obtain the common sources S. The problem with the approaches previously described is that they do not optimize a proper likelihood. Therefore, they do not benefit from the advantages of such estimator like statistical efficiency. Let me introduce MultiView ICA. MultiView ICA is a model with a closed-form likelihood and comes with a fast optimization algorithm. We have theoretical guarantees that our model is robust, and experimentally, we see that our model outperforms all other groupICA methods on various experiments involving two different neuroimaging modalities. Our model sees the data recorded by the subject-specific sensors as a linear combination of shared independent sources plus noise. Importantly, the noise is on the sources and not on the sensors. Now, our model can just be seen as a special case of noisy ICA. But let me try to convince you that this special case actually allows us to solve problems that are impossible to solve for general noisy ICA. So we'll just assume a similar model as ours, but with noise on the sensor side. As we see, the likelihood involves an integral, but the integral does not factorize. This makes the problem quite difficult and intractable in general. In contrast, I will show that our model has a closed-form likelihood. Like in noisy ICA, the likelihood involves an integral over the sources. We can factorize the first term in the integral because the subjects are independent given the sources. The second term we can factorize because the sources are assumed to be independent. We then perform a change of variable where xi is replaced by wi xi minus s, where wi is the unmixing matrix, which is just defined as the inverse of the mixing matrix. We then make use of the Gaussian assumption on the noise. We then leave out the product of wi and transform the exponential of the sum in red into the product of exponential. Interestingly, the integral is now factorized. It only depends on the product of one-dimensional integral. So in order to better see what's going on, let us just put the product into the exponential in form of a sum and just rename WGI xi into yij. We'll just call the integral I and let us focus on it for the moment, and if we're able to solve it, then we're able to find a closed form for our likelihood. So first we'll add and subtract this quantity in blue, which is the mean of unmixed sources. For simplicity we'll give it a name and call it Sj tilde. Looking further at the term on the left, we just realize that it doesn't depend on Sj, so we can leave it out of the integral. Then we have a remaining integral to solve, so we'll just make the change of variable z equal Sj tilde minus Sj. After this change of variable has been made, we see that a quantity appears that is remarkably simple. It is just the initial density convolved with the Gaussian kernel. Now that we have solved the integral, we can write the likelihood in closed form. What we write here is the log likelihood, which is minus log of p of x, and it's very simple to evaluate. And interestingly, when m equals 1, we recover the usual likelihood of maximum likelihood ICA. Now that we've found the log likelihood, we need to minimize it. To do so, we perform an alternate quasi-newton. We first fix all unmixing matrix Wi except one. And for the one that is not fixed, we perform a quasi-newton step. In our case, the quasi-newton step is a multiplicative update that involves the direction depending on the inverse of the Hessian. The exact Hessian is block diagonal, but each block is still too big to obtain a fast algorithm. If we look closely at this Hessian, we see this term yib yid, which represents the product of two components b and d of the unmixed data of subject I. Our approximation is to say that this product is 0 in expectation when b is different of d. And it's not actually such a huge approximation, because at convergence, yi is a good estimate of the source of subject I, and we've made as one of our assumptions that the sources are mutually independent. With this inverted Hessian, the direction is super fast to compute, and therefore we have a very fast algorithm. Now, let us look at the theoretical contribution we've made. First, we show that MultiView ICA is identifiable. We'll take the usual assumptions in ICA and just assume that at most one component is Gaussian and that sources are independent. Then we show that there exists one scale and permutation matrix that is global and doesn't depend on the subject, such as we can recover the correct mixing matrices. Our second contribution is about the noise level sigma that naturally appears in our likelihood. So first we make a technical assumption on the log density of the sources that is checked in practice, and then we assume that the data follows the model but with a different noise level than the one in the model and a different density than the one specified in the model. And even though we have different density and a different noise level, the algorithm is still able to find the correct mixing matrices because they are a stationary point of the log likelihood. So we've made this synthetic experiment where we generate data according to a Laplace density and with various levels of noise from 10-2 to 10, and then we fit our model with a different density and a noise level that is always fixed to 1. What we see is that our model uniformly performs better than other models. And we can actually see in practice that our model is robust to a bad setting of hyperparameters. So what I've presented here is a principled approach to perform groupICA. It has theoretical guarantees and it yields better results in practice. Of course it could be improved, the subject-specific noise model is particularly simple and it could be more complex. And also the optimization algorithm could be made a bit faster. We've made so much more experiments than this, involving multiple neuroscience modalities. I'll leave you with this beautiful image where we've localized and identified using MultiView ICA the common source through the make data of 200 subjects exposed to a audio-visual stimuli. Thanks for listening and have a good day.